During transmission, these are the original bits which have been sent to the receivers. But wait, what happened on the receiver side? The first bit has changed from 1 to 0. So one single bit error can change the meaning of entire data. So let us see how Hamming code can fix this error. So it is an error detection and correction code which can detect and correct up to 1 bit errors. Let's understand with an example. We are given the data word 1011. How many bits it has? What is the size? So m is equal to 4. What we have to do? We have to construct a Hamming code for 4-bit data word so that we can detect errors on the receiver side. Now we know that these are the data bits, but we have to add some redundant or the parity bits, also called check bits, and that is basically R. So how many bits should be added? So for that we have this equation. In the next slide we will understand the significance of this equation, but for now let us determine the value of R. So let R be equal to 1. You can also start from R equal to 0. So 2 to the power of 1 is greater than equal to M is total number of bits, data bits, that is 4. Redundant bit is said to be 1 and then plus 1. So this side gives me 6. What happens on the left hand side? 2 to the power of 1 is 2. But this equation is not satisfied. 2 is not greater than or equal to 6. So R can't be 1. So let R be equal to 2. So 2 to the power of 2 should be greater than equal to 4 plus 2 redundant bits plus 1. So this gives me 7. But on the left hand side, I just get 4. So this is also not correct. So let R be equal to 3. So 2 to the power of 3 should be greater than equal to 4 plus 3 plus 1. So this gives me 8. And on this side also I get 8. So 8 is equal to 8. So this is true. So we will finalize the value of R to be 3. Right? So I can just write, let me write over here. So R is equal to 3. But before we move further, let us understand what is the significance of this equation. See, each parity bit is responsible for checking certain positions within the Hamming code. So for with R bits, we can generate 2 to the power of R different patterns. So what is meant by pattern? So for understanding, let us see that this is the original string and this is Hamming code. For just now, remember that these three are data bits. This is a redundant bit. This is again a data bit. And these two are redundant bits, right? Now, on the receiver side, this string, there can be many cases or patterns in which it will receive this string. First pattern is no error. So this is same identical string received by the receiver. So there can be only one case in this case. Okay, so that is why it is one pattern. So that is why it is plus 1. Now there are 4 data bits. So each of these bits can go wrong. So let's suppose in this case, this data bit has gone wrong and rest is same. In the second case, this data bit has gone wrong. If it is 1, it will become 0. If it is 0, it will become 1. Rest is same. In the third case, this bit has gone 0. This bit has changed and rest of the bits are same. And in the fourth case, this particular data bit has changed, right? And rest is same. So that means there are 4 cases where data bit can go wrong. That is why it is 1. Even the redundant bit can go wrong. That is why it is plus R. So redundant bits are 3. So there can be 3 cases. 1, 1, 1. So data bits will remain same in all these cases. But in the first case, the first redundant bit has become 1 and rest is same. Right? In the second case, this redundant bit has changed. And in the third case, this particular redundant bit has changed. So these are 8 patterns which can be any one of these 8 patterns can be received by the receiver. So that is why it is, how many patterns are there? 1. These are 3 cases. So 4 plus 3, 7 plus 1. So m plus r plus 1. So 4 plus 3 plus 1. 8 patterns. So that is why there's 2 to the power of r patterns. So 2 to the power of 3 is 8. So this value of r should be such that it should be able to generate these many patterns. Right? 4 patterns for data bits, 3 patterns for our 3 redundant bits, and 1 pattern for no error. So what is the total size of Hamming code? M is 4 and R is 3. Our Hamming code will be of 7 bits. Right. Now here we have to determine the position of redundant bits, right? So we know total number of redundant bits are 3 and total there are 7 positions. Now these positions will carry both the data bits as well as the parity or the redundant bits. Now for redundant bits, the position in these locations will be powers of 2. That means if you write some power over here, you will get some answer like 2 to the power of 0 is 1. So we will check whether 2 to the power of 2 is equal to 4. So we know 1, 2, 4, 8, 16. These are the powers of 2. So here for one position, 2 to the power of 0, that is equal to 1. So this is the power of 2. 2 to the power of 1. This will give me answer 2. So this location. Now here we don't have any such power which will give me answer 3. In case of 4, yes, 2 to the power of 2, that will give me 4. So these 3 locations, they will be occupied by redundant bits. This is R1, this is R2, and this is R4. Now for the location 3, 5, 6, and 7, we have data bits in these locations. So this is D1, D2, D3, and D4. Now for this 1011, this is D1, D2, D3, and D4. So we have to read in this direction from least significant bit onwards. Now, this is what we have got. We have fitted the values of data bits, but what about redundant bits? Redundant bit will be either 0 or 1. So we have to follow the principle of even parity. Each bit will control certain positions within this string. We have to count the number of ones. If there are odd ones, then our parity bit will be 1 so that it becomes even. If it is already even number of ones in that group of bits, then it will be 0. So let's see. So this is the basic principle. But before that, we will understand this chart. Here you have to just generate the binary table. This is the code for 0. The code for 1 you know is 001 and for 2 it is 0010. This is just 4-bit code. But you also know that for this location 2 to the power of 0, it is just you have to write alternating ones and zeros. This is the position 2 to the power of 1, that is 2. So 2 times 0, 2 times 1. 2 times 0, 2 times 1. So see, this is the binary code of 3. And this location is 2 to the power of 2. So that is 4. So 4 times 0, 4 times 1. And last is 8 times zeros and 8 times 1. Right? So this is what we get. Now, where this table is going to help? This will help me to determine which redundant bit will control which particular positions in this string. So let's see for R1. So for R1, just check out this column. Just check out the locations where the bit is 1. Right? So position 1. So this is our redundant bit location. Right now this is empty. But then we have the location number 3, that is this position. Then 5 and 7. 3, 5, and 7. So it will control these positions. Right? For R2, you have to look for this column. So just see where, in which locations have value 1. So that comes out to be 2. So 2 is for your redundant bit, and the rest of the 3 locations are 3, 6, and 7. For R4, you have to look into this column. So just see, these are the locations where we have value 1. So that comes out to be 4. This is our redundant location. And then 5, 6, 7. 5, 6, and 7. So this is what we get, right? So now you have to count number of ones in each of these groups. Just leave this redundant bit. So here bit 3 is 1, bit 5 is 1, and bit 7 is also 1. Count number of ones. That comes out to be 3. Is it odd? Yes. So R1 will be equal to 1. So we'll set R1 value to be 1. Now see, this group will have 4 ones, so that is an even number. For the second R2, see, this is 1, position 3. At position 6, we have 0. And at position 7, we have 1. How many ones are there? 2. So this is already even. So we will make R2 as 0. So that this group has even number of ones. What about the last case? This is our redundant bit. What about 5? It is 1. What about 6? It is 0. And for 7, it is 1. Right? So this is also 2. So it is even number. So R4 will be 0. Clear? So this is what we get. Here R1 is 1, R2 is 0, and R4 is also 0. And now this is our final 7-bit Hamming code. One more important thing. Here we were counting the number of ones in each group. How computer perform this operation? It performs the XOR operation. So let us see for R1, right? It is 1 XOR 1 XOR 1. Now for XOR we know 0 0 is 0, 0 1 is 1, 1 0 is 1, and 1 1 is 0. So 1 1 is 0, XOR 1, that will give me 1. So answer is 1 over here, right? But let's see one of the cases, either R2 or R4. So let me just clear this out. For R4, it can be like this. 1 XOR 0 XOR 1. So 1 XOR 0 is 1, and 1 XOR 1 will be 0. So that is why we got 0, right? So here let me fit these values. This is 1, this is 0, and this redundant bit 4 is also 0. Input. So these are our data bits and these are our redundant bits. So 7-bit Hamming code. So this is our code word. Now let us see what happens at the receiver side. So this is our original code which was sent. So let us assume that the code has arrived with an error at location 3. Originally it had 1, but it got changed to 0. So bit 3 is wrong. Let us see how Hamming code will detect this error. So here we are going to count again. This R1, this is the group of bits for R1. These are the group of bits controlled by R2, and these are the group of bits controlled by R4. This time when we count, we have to count the R1 also. Okay. So R1 is 1. Then this location 3, we have 0. Location 5, we have 1. And at location 7, we have 1. So how many bits? 3. So this is odd number. So R1, we will just set over here in a separate table. We'll make it 1. So now when we make it 1, we will have 4 bits, right? Then here we have 2 is 0, 3 is 0, 4 is 6 is 0, and 7th location is 1. So it is again odd. So we'll put 1 over here so that it becomes even number. So here we have 4, that is 0, 5, fifth location has value 1. See, this is our fifth location. Sixth location has value 0 and seventh location has 1. So it has already two ones. So this value will become 0. Now see very carefully. 0, 1, 1. This is the binary code. Which decimal number it represents? 3. So this is the binary code of value 3. And where is our error position? It is 3. So from this binary code, it detects that error has happened at location 3. How to correct it? You know, simple rule, 0 will change to 1 or 1 will flip to 0. So let's see what is this value. This is value 0. How to correct it? We will just change this value 0 to 1. So see, now this code will match with the original. So this is the original code. This was the code word received by the receiver having 1-bit error at this location. And this is what is the corrected Hamming code. And that matches with the original code which was sent by the sender. Thank you.